Now, let's look at the relationship between these. If we have a modulus of 4 and an argument of the complex number being 60, I want to find the rectangular form of this complex number. So I'm going to go ahead and plot this first. So fourth ring out, 2, 3, 4, 60 degrees is pi over 3. Most of the time, if not always, angles will not be given in degrees, but they'll be given in radians. So here is my complex number z. And what we're wondering is, what is the x and y coordinate for this? Well, we can use trigonometry. We know that the y side of this right triangle that I can create here is the modulus, in this case 4, times the sine of pi over 3. The modulus times the sine of the argument. The x-coordinate, right here, would be 4, the modulus, times the cosine of the argument. So the rectangular form of this complex number z would be 4 cosine pi over 3 plus I times, or 4i times sine pi over 3. And when we get it in rectangular form, we don't want sines and cosines and angles in it. We want just an x and y coordinate. So we're going to go ahead and simplify this. We're going to take the cosine and the sine of these two angles. I'm going to take the 4 out just for fun. Cosine of pi over 3 is 1/2. Plus I times sine pi over 3. Sine pi over 3 would be square root 3 over 2. So our rectangular form would be 2 plus 2 square root 3 times I. Now, the modulus argument form of a complex number involves the modulus and the argument. Go figure. Well, that's like what we have right here. And there's a simplified form for this. The polar form, or modulus argument form, will be r, the modulus, times cosine theta plus I sine theta, where theta is the argument of the complex number, and it's abbreviated with CIS, cosine I sine. It's abbreviating that stuff together. Shorter way of writing it, but know that it means that. And that, ladies and gentlemen, is a very big idea for us as we move forward through this section. So here is an example. We have a rectangular form complex number right here. There's z. And we want to turn this into modulus argument form or polar form. Well, how are we going to do that? I like to draw a picture. Here we go. So that complex number on an Argand diagram would be in quadrant 2, where the real part is negative root 3 and the imaginary part is 1. The modulus, or r, is equal to the square root of 1 squared plus negative root 3 squared. So the modulus is 2. We're going to use the positive root there. Our angle theta, what we're doing is we're looking for an angle in quadrant 2, so we know it has to be between pi over 2 and pi. And to find that, we're using inverse tangent. And I'm just going to use the positive value of the sides, 1 over square root 3, because that'll give me my reference angle over here in quadrant 1, and I'm going to do pi minus that because I'm that much less than pi radians. And what we end up with is pi minus pi over 6. Our argument is 5 pi. over 6. So in polar form, z is equal to 2 times cosine 5 pi over 6 plus I sine 5 pi over 6, or simply written 2 cis 5 pi over 6. And bear with me, we're going to go a little further looking at this new polar form of complex numbers. We're going to look at what the opposite, the conjugate, and the opposite of the conjugate would be in this polar form, because it's very, very easy to figure out. So the conjugate, z star, would be x minus yi. So that would have a positive real part and a negative imaginary part. So that would be down here in quadrant 4. So the modulus stays the same. The angle, the argument, would now just be the opposite of theta. Opposite of z, that would be down that direction. That's opposite. We'd have negative x minus yi. That's a third quadrant complex number. So we have r still. CIS, there's that theta that we have. It's that much bigger than pi. So pi plus theta. And then the opposite of the conjugate would be back over here. That's going to be opposite x plus yi. So second quadrant, we're still going to have the same modulus, but now our angle will be theta degrees, or will be theta radians less than pi. So in general, we can make these statements. And the last thing involves scalar multiples. If I have some complex number, z equals r cis theta, alpha, a scalar, alpha is a real number. If we do that and multiply by z, one of three things is going to happen. If alpha is positive, all we do is make the modulus that many times larger. The argument stays the same. But if alpha is negative, we're going to take alpha times r, so now the modulus is negative, meaning we're reflecting through the origin. So if there's z with a modulus of r, negative r would take me that direction. So now I'm in the opposite quadrant, and that's why we have theta plus pi. And lastly, if alpha is 0, well, 0 times anything is 0, even in the complex world. So there we go. We are stopping here. The next video, we get in how this can help us to multiply, divide, take roots, so on and so forth, and we get into some truly beautiful stuff.